All right, let's jump right in. We're going to play environmental detective for a bit and try to crack a case that's, believe it or not, about 100 years old. The mystery of a river that's literally running out of breath.
I know it sounds a little dramatic, right? A river suffocating, but it's a totally real and very serious problem. See, when a river gets polluted, it starts to lose the oxygen that everything in it needs to survive. But here's the thing, the damage isn't spread out evenly. Nope. Somewhere downstream, there's one exact spot where things are the absolute worst. And our mission today is to find that spot.
So to figure this out, you've got to start thinking of a river as, well, a living thing. It's this incredible system that's always trying to keep itself in balance. And a huge part of that balance is dissolved oxygen. For all the fish and aquatic life, this stuff is just like the air we breathe. It is absolutely essential for them to survive. And just to be clear, we're not talking about the O in H2O. This is oxygen gas dissolved in the water. If there's not enough of it, the whole ecosystem can just fall apart. This slide really lays out the core conflict perfectly. I want you to think about the river's oxygen supply like a bank account. You've got two things happening. On one side, you have the oxygen eaters, deoxygenation. This is the waste and pollution, and it acts like a massive, sudden withdrawal from your account. Then, on the other side, you have the oxygen givers, re-aeration. This is the atmosphere slowly putting oxygen back in, kind of like a tiny, steady paycheck. The entire health of the river comes down to this constant battle.
So let's start with the bad guy in this story, the oxygen eaters. What's actually doing all the damage?
Well, it all comes down to a concept with a kind of technical name, biochemical oxygen demand, or just BOD for short. Basically, BOD is just a way to measure how much pollution, we're talking things like sewage or factory waste, is floating around in the water. And here's a great way to think about it. That waste, the BOD, it's like a giant all-you-can-eat buffet for bacteria. The more waste there is, the more these tiny bacteria show up for a feast. And as they're chowing down, they're breathing. And they are breathing in a ton of that dissolved oxygen, the very same oxygen that the fish need to survive.
Okay, the river isn't just a sitting duck. It actually has a way to fight back. It has its own built-in life support system.
And that system is called re-aeration. It's really just a natural process where oxygen from the air literally dissolves back into the river at the surface. You can think of it as the river's way of taking a nice, deep breath to try and get back what it lost.
Now, this is the really critical part. A fast, choppy, turbulent river is way better at breathing than a slow, calm one. But, and this is a big but, even at its absolute best, re-aeration is a slow and steady process. It just can't keep up when a huge slug of pollution gets dumped in all at once. The oxygen eaters are just way too fast for the oxygen givers.
So you've got this epic battle going on. How in the world do you predict who's going to win? Well, that's where a couple of brilliant engineers came into the picture about a century ago.
Their whole approach started from a really simple, logical place. The total change in oxygen in the river has to be whatever is gained minus whatever is lost, right? So they just needed to figure out how to describe the rate of both of those things with math and then stick them together into one powerful equation.
And that equation has a few main characters. You've got L naught, which is just how much pollution you start with. Then there's D naught, which is how much of an oxygen hole you're starting in. But the real action, the real tug of war, happens between these last two. Kd, the rate of deoxygenation, that's how fast the bacteria are eating, and Kr, the rate of re-aeration, that's how fast the river can heal itself. And when you put it all together, what you get is the dissolved oxygen Sag equation. You'll also hear it called the Streeter-Phelps equation, named after the two guys who came up with it. And get this, it was first published way back in 1925. It's this beautiful piece of science that we still lean on heavily today.
Okay, so we have the equation. How does this thing actually help us find that danger zone we talked about at the beginning? Well, here's where it gets really cool. When you take the results from that equation and plot them on a graph showing the distance downstream, you don't just get a boring straight line. You get this very distinct shape, a curve, a dip, a sag. And this visual, this dissolved oxygen sag curve, is the key to everything.
So let's follow the water downstream. Right at the discharge point, that bacterial feast kicks off, and the oxygen level just nosedives. That's the beginning of the sag. This is where the oxygen eaters are totally winning. After a while, the oxygen level hits rock bottom. That's the absolute lowest it's going to get. But then, as the pollution starts to get used up, the river's slow, steady breathing, that re-aeration, finally starts to catch up. and you see the oxygen levels slowly start to climb back up.
And that lowest point on the curve, that has a very important name, the critical point. Now, this isn't just some abstract point on a graph. For a fish, for anything living in that water, this is the most dangerous spot in the entire river.
And here's why that is so important. There's a certain minimum amount of oxygen that fish need to survive. What this equation does is let us calculate the exact location where the river's oxygen will dip below that life or death line. It takes this huge, messy environmental problem and makes it predictable.
You know, this is so much more than just a neat little classroom exercise. This equation has had a massive, real-world impact for almost 100 years now. I mean, think about it. With this tool, you can predict exactly where and how bad the oxygen depletion is going to be. You can pinpoint that critical danger zone. And maybe most importantly, it gives environmental engineers the power to go to a factory and say, look, you can only release this much waste. Any more and the river's oxygen is going to drop to deadly levels 5 miles downstream. It is literally the foundation of modern water quality management.
And that really leaves us with one big final thought. The Streeter-Phelps equation is an absolute masterpiece for dealing with a single source of pollution, like one pipe dumping waste into a river. But the threats our rivers face today, they're way more complex, right? We're talking about runoff from huge farms, pollution from entire cities, stuff that doesn't come from a single pipe. So the real challenge for the next generation of environmental scientists is this. How do we take the brilliant ideas from this century-old equation and adapt them to protect our rivers from the widespread threats they face today?